Hello. What we're interested in now is a matching algorithm. We have a set of model lines, we have a set of data lines. And what we would like to see is whether those data lines satisfy an instance of that model. And essentially, does it map, those data lines match that model? What we're going to look at here is what's called the interpretation tree matching algorithm. And it's one of the early systematic matching algorithms in the area of computer vision. It's a complete and exhaustive algorithm. That means that if there's a solution there, it will find it. And it works in a kind of discrete combinatorial way that we will see. But it's also a quite useful algorithm, particularly if you only have a small number of features in either the model or the data set that you need to match. So more formally, we're going to say we have a set of model lines. Okay, so these are, for example, the straight lines that we've been using. And although, in fact, it doesn't need to, we don't need to have lines. They could be anything, some sort of model feature and data feature. But here, we're interested in the lines that have come from our segmentation algorithm. And we have our set of image lines. Okay, and well, they're going to be in different coordinate systems. And there's going to be some sort of pixel to centimeter scale factor that we're going to need. And what we're going to want to do is really 3 steps. The first is make a correspondence between a model feature and a corresponding data feature. And then we're going to want to estimate the transformation that maps that model feature onto the data. So that's the rotation and translation that we keep referring to. And then finally, we'll want to verify that the correspondences and the transformations are realistic, that they've correctly mapped that whole model onto the data. So there's a verification stage. And once we've done all of that, what comes out is the identity object, because we may have more than one set of model lines for different models, different shapes. Remember, we have 3 different shapes that we're looking at here in our examples. And so we can say which of the shapes it is and what's the position of that object. In this lecture segment, we're only going to look at the model matching algorithm, and in other segments, we'll look at the pose estimation and the verification phases. So let's look at that matching algorithm in a bit more detail. So we've got our model features, we have our data features, and we're effectively going to do a complete search through all possible matches between the model features and the data features, just to find all possible ways of matching these features together, just to make sure we don't miss any matches. And this is a kind of general artificial intelligence search type algorithm. It's effectively a depth first type search, and if there is a match, we're going to find it. Now, unfortunately, we're going to have to extend our search algorithm with a kind of a thing called a wild card, or we'll sort of use it symbolically like a little star right here. And the reason for that is that our data is not perfect. Our model may be perfect. We have a whole set of edges that describe the object, but the data won't be perfect. As we've seen, sometimes we miss an edge. Sometimes when we segment the edge, it gets broken up into too many small pieces, or sometimes maybe just a corner gets missing or whatever, and then 2 edges get merged into one. And the net result is we may have too many data features or too few data features. And so finding an exact match for one of the model features may just not happen. And that's where the wild card comes in. Is that wild card allows you to match a model feature with anything, except well, actually says with nothing. It just allows you to say, well, we can just carry on as if we matched it and go on to find matches for the rest. As mentioned here, there's other reasons why you might need that, and that is the case of occlusion, where you may have one object on top of another, and therefore you can't see all of the features. Here we're looking with nice isolated objects, and so that's not going to be a problem. But the other segmentation failures are actually problems. Well, because we're dealing with exhaustive matching, and we have objects that sometimes have a variety of symmetries in the shape, this may mean that we may get multiple matches. You know, if you imagine 2 squares matching together, they will match together with 4 rotations. And in fact, you can then flip the square over, and then you have 4 more possibilities. And we're going to encounter all of that here. Also, our matching algorithm is going to use some geometric constraints to help control the matching, but they're not very strong constraints. And what this will mean is that we get matches that are invalid, and therefore they will be eliminated when we do the verification stage, but in the meantime we're sort of carrying them along. We'll see that later when we look at the example. Anyway, the net result is a solution can be found if there is a solution, and that will consist of a set of pairs of matched model and data features. So let's see how we can find that. Well, as I said, this is a kind of search tree sort of problem. So here's an example of the search tree that we get. We start at the root node with nothing matched, and at each level of the tree we attempt to match one additional model feature. So here's the first model feature, the second model feature, all the way down to the last model feature. And it's exhaustive matching, so therefore we say, well, in order to match this model feature, I need to see whether it matches with this data feature or this data feature. So we try all possible data features, and then finally we also have our wildcard, because maybe none of these data features are the appropriate ones to match with that model feature. And then for each of the successful matches, actually I should say we will find reasons to throw away some of these matches right here in a few minutes. We'll see how to do that. And but for each of the successful matches, we then go down to the next level. So let's say data feature D2 has successfully matched model feature M1. Well, then we want to go down to the next level and now find a match for model feature M2. Again, we exhaustively compare all of the data features and the wildcard, and if we have a success there, then we go down to the next level, and so on, until we get down to the root of the tree, and then we've, not the roots, the leaf nodes of the tree, and then we've successfully found a set of matches for all of the model features. So that's roughly how the algorithm works. We're going to search through this tree and find all of the matching features. And not just finding one path, then we also back up and then find other paths. And anytime we get all the way down to the foot of the tree and the leaf nodes, then we found a successful set of matches. Well, this can potentially be quite a complicated tree. If you have any experience of artificial intelligence algorithms, you know that the size of this tree is exponential, and if you have any experience of computational complexity, you'll know that exponential algorithms really cannot work on a very large amount of data before the computation required just becomes too much to be realistic. So we want to look at ways that reduce that search complexity. And in fact, we don't actually need to consider all the paths in the tree. And we've got 4 different rules for helping prune the search tree. And what I mean by that is that when we get to a particular node in the tree, what that means is we can determine whether, given the set of pairings so far, is this likely to be a valid or invalid set of pairings. And if it's an invalid set of pairings, we can throw that away. And as well as throwing that away, it also throws away the whole subtree that lies underneath that node. And as a consequence of that, we really can eliminate a lot of search from that space. So I said that there are 4 different ways that we can prune that search tree. The first one is what's called the unary test. And we're going to assume that we've gotten down to a certain point in the tree, down to level K, successfully pairing features, and we've got model feature I to data feature J sub I already paired up. So we've got K of these pairs already. And now we're in the next level, and we want to say, well, should we extend this by adding this new pair, so a new model to data feature pairing? Well, at this point, we're going to apply our 4 tests. The first of the tests is the unary test, and it basically says, is this model and data feature compatible with each other? Here this is done in a kind of abstract sort of way, but you can imagine that if we're matching up lines together, then the test that we're going to look at is, do the lines have the same length, or approximately the same length? If one is very long and the other is very short, then they're not compatible. It seems highly unlikely that they could have been matched. They could have come from the same object. Okay, so that's the unary test. We'll look a bit more about that in particular for our shape matching case coming up. The second test is a binary test. And this says, for our new features, let's pick one of the pairs of the previously matched features. And are the new pairing of features compatible with the previous pairing of features somewhere on that path? And if they're not compatible, then we terminate the search at this point as well. In fact, this is one of the more powerful tests because it not only compares this pair with this pair, but it pairs with all of the pairings on the path down to the current point. So if we're doing a match down here and we'd want to do our binary test, we'll do the binary test with this new possible pairing and all of the previous matches that were successfully made all the way along that path. And since we're doing a lot of tests, that tends to throw out a lot of the invalid matches. The third way to prune the tree is to use what's called an early success limit. And that's saying that we don't necessarily need to go all the way to the bottom of the tree. We may say that once we've got enough features paired, that gives us enough information to go on and do the pose estimation and the verification stage. And in fact, for the kinds of shapes that we've got here, probably 2 or 3 is all we really need. And since the search tree is exponential, that means the further down you go in the search tree, the broader that search tree gets. And if you can limit the depth to which you go, then that's, it makes it possible to do a great deal of pruning. The final constraint that we can use to help prune this is what's called the early failure limit. And this is also related to the early success limit. It's the same parameter right there. As you're going down the search tree, you can keep track of how many real pairings have been made, how many pairings that you've made that haven't used the wild card. And if you get to a certain point in the tree, you can say, well, how many real pairings have I made? And how many pairings could I continue to make if I went all the way to the bottom? And if the two of those together are not going to be enough to reach your early success limit, then that means you're never going to get enough matches to be able to be satisfactory. So you might as well just stop right here. Okay, and again, because that is pruning off the bottom of the tree, which is where most of the nodes are, that can be quite effective in reducing the amount of search, the amount of tree search. And so, according to the limit and where we currently are and how many model features, there is a constraint test that tells us whether or not we can fail at this point or whether we should continue to do our matching. So those are the four constraints that help prune the tree. And now we're in a position to sort of look at the real computational complexity of this algorithm. So potentially, if we had our M model features and our D data features, plus the wildcard, potentially, in the worst case, our search complexity is this exponential number right here. And that's really too big to work with. So let's see if we can simplify that analysis a little bit using these constraints we've got. So the first is a probability value, and that's the probability that any two randomly picked model and data features will somehow satisfy the unary constraint that we've defined, whatever that constraint may be. Because you can imagine, some line segments are longer and shorter than the other, and so even though the two segments maybe are not supposed to be matched, they may have lengths which are sufficiently compatible. So there'll be some probability of that. Okay, and this is the probability that you just sort of randomly get a match. The second probability is related to the binary test, and that's the probability that a randomly selected pairs of models and data features will successfully pass that binary test. Of course, you always want the real data to pass the test, but sometimes other data, other correspondences may pass the test as well, particularly if your constraints are not very rigorous. And so therefore some will pass. The fewer that you can pass, the stronger the constraints you have means the fewer that will actually pass, and that's better because that prunes the tree maybe to the point where it only finds directly the correct model. Nonetheless, with these two conditions, we can then look at the computational complexity. And a nice analysis by Grimson showed that if the number of model features times the number of data features times this binary probability was less than 2, then the average case complexity is given here with this order of LD squared. So generally L is some sort of function of the number of model features, so you can kind of think of it as like MD squared as well too. So it's kind of a cubic sort of algorithm in the number of features. But and cubic is not good, but cubic is immensely better than exponential the d to the m case that we have right up here. And altogether what this means is that for reasonable numbers of features, say up to 10 or something like that, the amount of search that you can do is a manageable sort of number. So we're going to look at that algorithm that I've sort of hand wave a little bit with my search tree, and we're going to look at that in a little bit more detail by showing you kind of the core of the MATLAB that implements that algorithm. And the full code for that algorithm is available on the web page associated with the video here. Right, so the function that we're going to look at is this I tree, the interpretation tree, and it's got a number of parameters. So this is the model identifier, and this is the number of lines in the model, and this is going to be a recursively implemented type algorithm. So we're going to enter with the level at which the last model feature was matched, and then we're going to here's our early termination limit, and then these two are kind of the results that we get, the pairings between the model and the data features, and the number of those features which are paired, and that's kind of arguments that get passed down the algorithm as we go through. We could have also passed the data down and the models themselves, but we chose here to use these as global variables, just so they're all constants, so they didn't really need to get passed in as arguments to the algorithm. So we've come into this tree at a given point. We've already done a certain amount of matching, and the first thing we're going to do is we're just going to check our early termination limit. So if the number of pairs that we've made is greater than or equal to the termination limit, then we're in a position to say, right, we're probably in pretty good shape, and then we're going to go do the next stages, which is the estimate, the pose, and the verify. So we'll see the actual algorithms for estimating the pose and doing the verification in another lecture, but here we've got the code for it. So we pass in the estimate pose, we pass the model, and we've got the pairing between the model and data features. That gives us our estimated rotation and translation. It turns out the algorithm that we used produces 4 different candidate solutions. So we have to check each of those 4 solutions in our verification algorithm. We pass in our rotation, our translation, our model, and our pairings. And we attempt to verify, and if we do find a successful verification, then we can return and say that our algorithm is done. And if not, if we get down to here, then our algorithm has failed to verify, and we kill off this branch of the tree, and then we return to the search algorithm. We kind of pop up from our recursion. Anyway, all this bit right here, that was in the case where we hit the search limit successfully. So that's one of our 4 cases. The next case is the early termination limit. So here's the formula that we have here that we check for the early termination. And if the early termination is fails effectively, then again we exit and return back to our search algorithm. So those are the 2 early cases. And now we're into more of the normal sort of case. That's where we want to extend ourselves down to the next level by matching a new data with the current model feature. So we increment the model feature to get to the next level. We search through all of the data features by iteratively just looking at each of them one by one. We try each of those data features matched against the current model feature in our unary test. And if that is successful, we go on to the binary test. The binary test, we need to check for all of the pairings previously made along the current path. So that's what this loop is all about. And we do the binary test from each of those. And if it fails for any one of them, we reject that. We don't need to pass all of them. We need to pass all of them. If any one fails, then the match is no good. If we have successfully passed the unary test and the binary test, then we record the pairings in our sort of array right here, and then we recurse down to the next level of the tree where the whole search process begins again with a new model feature. If coming back from that we've had a successful verification, then we return, otherwise we sort of pop back and continue the search. As I mentioned, we have a wildcard, and after we've gone through all of the possible data features matched to the current model feature, we now also need to consider the final case of that wildcard, and that gives us one more recursion. The only difference is we don't increase the number of matched segments that we paired together. So here we made a pairing and we added one to that because we've made one additional pairing. Here we pass the number of pairs that we've got already down to the next level and just skip the current model feature. For those people who like to see algorithms a bit more visually, diagrammatically, here we've got a kind of diagram for that. And here's a sort of a combination of the matching and the verification loop. We've got our matching algorithm. We look for another match. If we reach the termination condition, we go down. Otherwise, no, we recurse and bury in. If we do reach the termination condition, we go down to the verification stage. If we have a successful verification, we exit. If we have an unsuccessful verification, we kind of come back and continue with our matching algorithm, searching more of the tree till we can potentially find a solution. Well, let's look at our specific example right here. We're looking at matching our T shapes together and our T or L shapes together, and we need to have a set of unary and binary tests to do that matching. So we're going to look at the specific test that we used for that matching right here. In the case of our the unary test, there's really not very much that you can use to describe the shape. In this particular case, all we have really is the length of the line. If we had colored objects or whatever, you could maybe use the colors on either side of the line, but here we've abstracted all of that away, and we just are left with the line segments themselves. So therefore, all we can really say is the length of the data line the same as the length of the model line? Now we have to be a little bit careful about this because our segmentation algorithm may have given us some data lines which are a little bit too short or too long, and therefore we need to add some tolerances into this. And the way we do that is that we have a tolerance that's sort of 0.3, and 0.3 tolerance on the length of the model line, and then the sigma here is again our scaling factor, which converts our model measurements in centimeters into pixels, and there's our data line. So this is if the line is too short, or if this test will fail, or if the line is too long, this test will fail right here. So that's the kind of constraint on the length of the line. So that's the unary test. It's not very strong. The stronger one is the binary test. The binary test looks for pairs of data lines and pairs of model lines, and looks for the angle between those lines. So here we see the angle alpha between the data lines and the angle beta between the model lines. And if these two angles are the same within some tolerance, then again this passes the test. And this sort of, the reason why we have this constraint comes from the geometry of the problem. Remember, we've got a shape and we've got a pair of lines right here, and the shape may be anywhere in the image. Okay, it could be different rotations or translations or something like that, but the angle between those lines remains the same, independent of the position of and rotation of the shape. This only works if we're working with a sort of fixed camera and in 2 dimensions. If we were working in 3 dimensions, of course, the shape may project out of the scene a little bit, and the observed angle won't be the same. But fortunately, we're looking with the rigid camera, looking down on the shapes, and only translations and rotations apply here that leave the angle identical. Another constraint that we could use, for example, in the binary test, is we could also limit the duplicate use of the model or the data lines. Our algorithm, as we expressed it right there, as we went down to a new model level, we allowed it to match with all possible data lines. Well, For example, you could say, well, let's throw out any data lines that we've already successfully matched and not allow them to be rematched. And indeed, you could do this, but it turns out that it hardly makes any difference to the computational complexity of the algorithm. So it's simpler just to kind of leave it in there. Right, so those are our two our unary and our binary constraints we're going to use. We need our early termination, either success for or failure limit. Okay, and we'll just say here, for the sake of argument, we need to match at least almost all of the model lines. We'll allow it to not have to match one of the lines to account maybe for some segmentation failures or something like that. Okay, we'll also allow it to try all the models in the data set because we don't know which object we're looking at to begin with, and we have 3 possibilities here. And we can just say, well, we'll stop at the first verified model instance for each of the models. Okay, and that's a perfectly reasonable way of setting up your matching algorithm. Well, here I loosened that a little bit and I said, well, let's go through and not stop. Let's go through and see how many things we can actually match if I allow it to run completely, fully, exhaustively all the way through to completion. And this is the results that we get here. We had 12 different images that we were looking at, and we had 4 shapes for each of those 3 different models, the T model, the thin L, and the thick L models. And this is a kind of table of what all it matched with. So the first image, which was a T, did successfully match with the T, but it also matched with the thick L. There was just enough correspondences that aligned more or less correctly, satisfying all the unary and the binary constraints between the 2 different cases. So it allowed these as possibilities. And this is why we need to have that verification stage, because clearly the thick L is not going to match with the T, but we need to have the pose estimation verification to eliminate these extra sorts of matches. And probably only one of these 4 matches here also ought to match, but we don't know which one until we've done the pose estimation and the verification. All right, so what have we got here? This is quite a long and complicated algorithm, and I know that's the case. But it's quite a useful algorithm, this interpretation tree matching algorithm. It's a general, discrete, exhaustive matching algorithm that if there is a solution there, it will find it. There are other matching algorithms that are more heuristic, that work more efficiently, but they do not guarantee that they will find a solution, whereas this one will find a solution if it is there. It can be a pretty good and efficient algorithm if we have good unary and binary tests that turn our large exponential tree into a kind of rather thin, well-pruned sort of tree. We've also only looked at this for flat parts where we have some straight lines and straight edges. And you might say, well, what about for real parts? That, well, if you look at the kinds of parts that people actually manufacture, actually this kind of algorithm will work for about half of those parts. And the reason for that is that, again, as I've said previously, when people manufacture parts, they're meant to usually fit together with something. And if you're going to fit something together, you're going to have some straight lines, or you're going to have some holes. And either the straight lines or the holes, or maybe some circular arcs sort of that will fit in, something like that, pegs or something like that. Each of these features are easy to identify and easy to work with in our matching algorithm. And from a manufacturing point of view, they're easy to manufacture and they're easy to fit together. So consequently, most parts, or well, many parts, will have these kinds of features on it, and this algorithm therefore can be used for those sorts of parts. Well, thank you very much.